Okay, this is the chapter on sound, speech, and hearing. First of all, we encounter all different types of waves. We can encounter waves in the water. We can encounter light waves, as we talked about in the previous chapter. We can also encounter various mechanical waves, though of course a water wave is a mechanical wave. But we have other types of mechanical waves, like, a wave on a rope or a wave in a spring, a variety of other things that are mechanical waves. In this particular chapter, we'll deal with sound waves, so these are also waves. Now, waves are periodic, they repeat, and they are called periodic waves. All sound waves are periodic. All sound waves, whether it's a sound from a guitar or a clapping sound, is periodic, but some waves are periodic on much shorter time scales than others. Let's consider transverse versus longitudinal waves. The difference in these is what these waves do to their medium. So a transverse wave makes the medium move up and down. Whereas a longitudinal wave makes the medium move side to side. So I like to think of the transverse wave as like when you have a wave at your football stadium, the people move up and then they go down, up and down, up and down. So these people are moving back and forth in a periodic fashion. Whereas if we were to do a longitudinal wave, it's like the people would lean together and then they'd move apart and lean together and move apart. So the longitudinal waves make the medium move side to side, make the medium move side to side. Now, sound waves are longitudinal. Well, let's look at simple harmonic motion. Simple harmonic motion is a type of motion where something oscillates with a force that is proportional, oscillates, that is proportional to the distance from the equilibrium position. I'm going to abbreviate equilibrium, EQBM. A good example of simple harmonic motion is a force on a spring. In fact, we often use this example as sort of a prototype for other things. Sound is also an example of simple harmonic motion. First of all, let's consider the force on the spring. You have a spring, I have some object on it. This is my X initial, if I drop this thing down to some X final, this difference in distance will cause the force to increase. In fact, we saw last semester, you did this in the lab, but if F is equal to kx, so that if x increases, then F also increases by this, excuse me, by the same factor. Now, for sound, in this case, the restoring force is offered by the spring, but for sound, the restoring force is the pressure of the surrounding medium. You see, let's say that we have a medium. So a medium is made up of different molecules, and these dots represent the molecules. Let's say that you take one of these molecules and you displace it slightly. So you put it over here for just a moment. There will be a restoring force from the surrounding medium that will want to put that molecule back into its place. And whether that medium is a gas or a liquid or a solid, there will be a restoring force. Now we'll see that that restoring force is actually larger for solids and liquids over gases because of the nature of the structure, that there will be a larger pressure to move those molecules or atoms back into their place. That's something we call elasticity. We'll get to that in just a bit. Okay, so let's look at a couple different definitions for waves: equilibrium, amplitude, period, frequency, and wave speed. And you'll need to know how to identify these and calculate these. But before we do that, we need to look at two different ways that we look at periodic motion or waves. Uh, the snapshot graph looks like this. And you know what? The history graph is going to look exactly the same. But they tell us different things. So the snapshot is a picture of a wave at a particular time. So this is at a particular time. And it shows the wave over a certain distance. So I see that I have position here. It shows the wave as it exists in space over a particular distance in space. There are a couple things that I can get from this. I can determine the amplitude. This is the amplitude. It goes from the equilibrium position. Oops, sorry about that. It goes from the equilibrium position up to a peak, or you can measure it in this way. Um, Hold on, I'm gonna have to pause this. I don't know what's. Okay, I'm sorry. We'll just carry on for a minute, but you're gonna have this little wind right here for just a minute, okay? So this is the amplitude. This is also our amplitude. We can also see the wavelength. The wavelength of our wave is the distance from one peak or one trough to one trough. So I can measure my wavelength in several different places. I can also measure it, say, here. Let's do this in a slightly different color. So if I take a point here, my wavelength is to here. I like to think of it in this way, that if I'm going down here, my wavelength extends to the next point where I'm going down at the same location. So that is my wavelength, one wavelength. All right, I can also look at a history graph, and a history graph, instead of giving a snapshot in time, gives a duration of time. So this is looking at one particular position and as it changes over time. So here I can get a couple different things. I can still get the amplitude, by the way, from this graph. I can get the amplitude in the way that it did before. I can also measure the period. The period, t, this is the time for the wave to travel one wavelength. All right, so the time for it to travel one wavelength is from peak to peak, or just like we did before, I can go from here to here, or I can go from here to here. All of those measuring time on the x-axis will be the period. Now, from this information, from the wavelength and the time, if the wave travels a wavelength in a time that's the period, then I can calculate the wave speed, and that is going to be wavelength divided by period. Now, I can also describe something called the frequency. The frequency is how many crests pass a given point in a given amount of time, and we find it just by saying the inverse of the period. So the frequency is simply the inverse of the period, and then we get another expression for v, which is equal to lambda times f. Now we'll see a little bit later that the wave speed, which is this value, is not dependent upon neither the wavelength nor the frequency. And you might think, well, gosh, that's kind of strange because you just told me that it's equal to lambda times f. But the wavelength is only dependent upon the medium. We'll repeat that in just a bit because it's fairly important. Excuse me, not the wavelength, the wave speed. The only way to change the wave speed is to change the medium. Okay, and so if I change, for example, the wavelength here, then I will change the frequency, but this will always remain constant unless I change the medium. All right, you should be able to answer these questions now, so take a moment there, and then we'll pick up with sound of a vibrating string. There is a video that you can watch if you want. If you don't want to, that's okay too. But it's fairly interesting talking about slinkies, and here he is talking about how waves travel down slinkies. I think it's more interesting than anything, but if you want to watch this, it's a Veritasium video, and it is right here. And hopefully next time, I think you're all winners, all right? But next time we will try to get rid of that win icon.